Hello YouTube, welcome to my channel, The Cyber Rancher. Today I'm going to show you a tool I created. And this tool, what it does is it shows how much a constructed wetland can purify water, reducing the loads of phosphorus and nitrogen. And the tool itself is works by entering in the flow of the river or stream in cubic feet per second, acres, days, and then your load of nitrogen or nitrate and phosphate or orthophosphate. And you enter in your values here and you run it. And what I'm going to do today is I'm going to just give you a quick demo on how to use this tool. And to provide a little bit of background about this project, I built this tool using Python back when I worked at the Idaho National Lab. And you could go to Idaho National Lab's GitHub page and download an open source version of this tool. And it was published, I think last year. It was put on their software page, the unsupported software page. And there's two different versions there. There's a Python script that you could just run on your own computer, and then there's also a script if you have an ArcGIS server. Both of them require ArcGIS interpreter and libraries, and so they're not, I guess they have some proprietary software requirements, but you could download those open source and see the models themselves. However, what I did today, or what I'm showing you today, is a version of the software that has been built from open source Python that didn't rely on the ArcGIS or ESRI technology, and I converted it into TypeScript. So the tool, it does the same calculation and it's a lot more user friendly, and you could use my web map application here to run it. And just to go over this web map application real quickly, you could turn on different layers here. So here I have U.S. flood hazard areas, I have BLM surface management area, and then I have national hydrology data set. So if you have data in here, you could use it. And HUC boundaries. And today we're going to be looking at the Portneuf HUC zone, and that's this watershed. If you look at the Portneuf watershed, it covers portions of the Fort Hall Reservation and a lot of Bannock County. And it basically starts on the Fort Hall Reservation, the Portneuf River itself, and it flows through the Chesterfield and Lava Hot Springs, and then down through Income, through Pocatello, and then it comes back onto the reservation again and goes in American Falls. And on its travel, sadly, it gets very polluted, highly polluted from the development and activities here, especially the Simplot phosphate processing plant here. And so where we're going to be doing this analysis, where I'm going to show you, it's going to be using real data, and I'm showing you how it works. And but it's down here that the Portneuf River flows through here, and it comes back on the res, and they have monitoring sites down here. So the data comes from this area, below Batiste Springs to be exact. And so you could also, with this tool, you could also turn on and off different layers, so you could better see. Like here's an aerial photograph, and basically we're going to be doing this analysis is down here. Here's the dam that the BIA, Bureau of Indian Affairs, diverts water for irrigation, and then it flows back on. It's onto the reservation here and goes down, and it gets. The issue with this river is that it gets so much pollution in it that the water becomes hypoxic, or there's a eutrophication that occurs. And I'm going to go over that with some slides a little later, but I just want to give you kind of an overview of this tool, the different things you could do right now before we get into that part of this discussion. And so here's a legend here. It tells you kind of what the different symbols and things are there. You could create a bookmark. So like if I zoomed in on here and I wanted to add a bookmark here, and we could call it Lower Portneuf. Click add, and then maybe you're messing around, zooming around, you could click on it, it'll zoom back in. You could also print it, and you could just click and export. It takes a second to generate, but it should give you a map here. Let's see how long it takes. There it goes. So makes a map, shows the legend, gives you a scale bar, all that good stuff. It also, when we use the tool, we're going to be using this measure widget. And what we do with this measure widget is we select the polygon area tool here, and we draw an area of where we're going to put our constructed wetland. You can convert it to acres, and that calculates your acres. So we're going to be using that data in this tool to make this wetland project work. Okay, so now I'm going to go into a little bit of a discussion on this tool and how it works and how we get the data and information to make the tool work. And so we're putting in good data, and we're getting out results that are relatively real world results. And so, like I said, we're going to be focusing on the lower Portneuf River. Here, there's Pocatello. These are the monitoring sites where they've been collecting this data on phosphate and nitrogen loads in this stream. And so, in case you don't know, what occurs with streams, and especially the Portneuf in particular, is when you have high levels of nitrogen and or phosphorus that go into these streams. Nitrogen usually comes in from like sewer systems or agricultural areas or animal feedlots, agricultural activities, nitrogen additions to farms, potato farms, things like that cause nitrogen to come in. And phosphorus, the same thing, usually comes in from agricultural activities. But in the Portneuf case, a large amount of the phosphorus is coming in from the phosphorus producing plant or phosphate refining plant that's located just right next to the Portneuf River. And so you have these nutrients coming in to the water, and the water gets sunlight, it gets warm and heated, especially during the summer, and you have a large growth of macrophytes or aquatic plants and algae. You have algae growth, and as it gets warmer and you got bright sunny days, you have a lot of algae growth. And what happens is that algae grows and it dies, and when it dies, it uses up oxygen and depletes the oxygen. And so what you have is water that becomes low in oxygen, and fish, it's so low that fish cannot survive in it, and then you have fish kills or dead zones because of the eutrophication that's occurring. Becomes hypoxic, I think is the term. So that's what's going on in the Portneuf River, especially during the summer months. Sometimes you hear about it in the news that there's fish kills, and in some instances, this is my theory, I'm not sure if this is exactly right, but you have botulism outbreaks out there, and botulism will grow on these algal mats, and the birds and stuff will get in there and they'll be eating stuff, and they'll end up eating some of that botulism, and then you'll have these big bird die-offs. And so it's a problem. And this shows a map of some of the issues associated with eutrophication and dead zones that are caused from algae growth and eutrophication. So this is along the Gulf, the Gulf of Mexico and the Dead Sea, and the red here shows dead zones. And so you could see like this is basically all dead zones where aquatic life cannot live very well, or can't live at all, I guess. And then this is the American Falls, and this is from the USGS showing the red shows where you're having these real high levels of algae growth and problems. And so you can see the Snake River coming in here very hot, and the Portneuf River coming in here very hot with eutrophication causing algae growth, and then it flows in. This is the Fort Hall bottoms here, and so you have relatively cleaner water coming in, and it's hitting here and it's mixing. But then I think what happens is the flow, it's going down, the flow gets down about here and it starts warming up, and it's been in the sun, starts warming up, and all those nutrients that come in, they start growing again, and then the flow comes back. It's like a big eddy here. And so this is all the algae growth. And you can see it if you go boating down there during the midsummer when it's hot. And so then you have here, this is some information you need for the Wetland Geoprocessor. So remember I was showing you earlier that one of the input parameters you need to know is how long are you going to be analyzing this, what period of time are you going to be analyzing this, the effects of the constructed wetland on reducing nitrogen and phosphorus. And so the user's got to enter in the number of days. And so in this analysis, we're going to be looking at July 1 through September 1, and that's 62 days. So we'll be entering that into the constructed wetland model, the Wetland Geoprocessor. And we also need to know the day of year it is, and that's the only reason we need to know that is because when we get to the Idaho DEQ reports, they report their values, their phosphate and nitrogen values by day of year. And so I put that down here. So July 1 is roughly 182 day of year on a non-leap year, and September 1 is 244 day a year. So you got to remember that. And then also here is the showing of the USGS gauging station, and it shows what the flows are like during that same time period. And so you could look at them, and roughly, you could see like on average it's about 200 CFS during this time period. And so that we need that value for our flow to enter into the Wetland Geoprocessor model. And so remember, like I said, we need to use that measure widget in the Wetland Geoprocessor. And so I did that here. I drew a polygon down there along the Portneuf River, and calculated it to be 100. I basically made my constructed wetland. You can make it any value you want, but in this case, I made it 178.57 acres. And then for the data, I wanted to use real world data here. This is older data. It's data from a 2010 Portneuf River total maximum daily load revision and appendum report produced by the Idaho Department of Environmental Quality. And basically in that report, they're reporting that the annual median load is 1.25 parts per million of orthophosphate at lower Portneuf River. And so this graph here, you could see these values. Oops, went back. You could see these values here, these circles. Those are your orthophosphate values that are being reported at different time periods. And if you remember, these red lines, they show those day of year dates that we talked about earlier. And so I think it was like 182 and 244 or something like that. But we're basically evaluating this time period. And so you would want to take the average between these numbers right here, these dots. So if you drew a line through them, a best fitting line, it's roughly, I don't know what we could say, maybe 1.4, probably 1.4 parts per million. Oh yeah, 1.4 parts per million roughly. And then as for nitrogen, unfortunately that DEQ report doesn't give nitrate separate. It keeps nitrate with nitrogen dioxide. It reports it together. So these numbers are probably a little bit elevated because they include nitrogen dioxide, which comes mostly from automobiles and their exhaust getting back into the stream system. And but if you look at this from the day of year values, the average is going to be somewhere through here. So July 1 through September 1 is about 0.3 parts per million. And if you notice, it's got this curve here. And I'm not exactly sure why it's like that, but I'm assuming that the plants and algae growth are using up some of that nitrogen during the summer months. and during the winter months they're not using it, so it's higher during the winter months. So we're back into the Wetland Geoprocessor web map application, and like I said, you could use these different tools to get your calculations. And where I built my constructed wetland, I was looking at this and I was thinking, I'll build it right here in this area, but in real world settings and things like that, you may or may not be able to build in these areas. Like I know down here in this area, it's on the reservation. Anywhere that's low like that are usually places that will have cultural resources and or other values, wildlife habitat, fish values. Maybe it's a grazing area, maybe it's owned by somebody. There could be a lot of different values associated there, but this is just an example. And so what I want to show is that anyway, I wanted to build my wetland here, so I'm gonna just kind of draw it out. This is what I hypothetically, like, let's say we wanted to make it like that. Okay, that would be where we divert the water, we build a constructed wetland in here, and we want to calculate how much does that constructed wetland reduce those nitrogen and phosphorus loads. Okay, and so in here we'll go back to our real world example, our data. And if you remember from our example, we wanted to use a CFS of 200, right? Because from the USGS gauging station, during that time period we were wanting to analyze, it was about 200 CFS. Okay, and so in this case we drew a thing of 177 acres, so we'll just enter 177.40, and we wanted to analyze it for 62 days. And we had a part per million of nitrogen at 0.3, and we had a part per million of orthophosphate, which by the way is really high. That's really high, of 1.4. That's very high. And then we want to hit submit, and this is our values. And so if you look at these values here, the nitrate removed from this constructed wetland here, if we built it, would be 4,818 kilograms would remove. So if you had that in there for 62 days, and it was a wetland that was 177.4 acres, it would remove 4,818 kilograms. And it would remove, for phosphate, it would remove 13,688. So let's just do a quick calculation for convert that into pounds, because I know a lot of you don't know kilograms. So for nitrate, 4,818 kilograms is equal to, in regard to pounds, it equals 10,621 pounds of nitrogen would remove from that kilogram, from that wetland. Now let's see, for phosphate, it would remove, let's see, we enter 13,688. It would remove 30,176 pounds of phosphate. And then, so your load, remember your load is for nitrate, it's coming in at 0.3. That would reduce the load of the river by to 0.14. And then it would reduce the remaining load of phosphate, it would reduce it to 0.95 here. Okay. And so, and this tells you the percentage removed. So the constructed wetland, it's more efficient at removing nitrate, 52.94%, and than it is phosphate. It's only able to remove 32.23% of phosphate. And then the constructed wetland tool also has a cost estimate. So like how much would it cost? And these cost estimates are based upon real world constructed wetland projects, and it includes a lower, a mean, and upper the lower is the lower confidence interval, the mean is the mean average price, and then the upper is upper confidence interval. So on average, basically the cost of this wetland would be roughly, let's see, $7 million to build that constructed wetland. The lower end, it would be 340,000, and the higher end, it would be 13 million to build it. And this is basically your cost per acre here. So cost per acre, the lower is $1,921 per acre. The mean is $39,716 per acre. And so this just gives you some ballpark. There's a big confidence interval there for the cost estimates, because as you can imagine, if you're building in an urban area, it could be really expensive, or like in California, or if you're building out in the middle of nowhere, rural area, it's not going to be as expensive. But that's the tool, and I'm going to show you a little bit about the equations and the models now. Now, if you want more information about the actual equations and how I built this model, you could click on this little eye icon here, information icon, and it'll take you to another web page. And it talks a little more in depth about how I built this model and where these equations come from. I can't take credit for the equations because they were created by Chang and Basu. And if you click on these links, it'll take you to the actual scientific papers that took the information from these different sources, excuse me, and utilize them. And this paper, this is the one it's primarily based upon, was published in Nature. And so if you don't know, the Nature journal is the biggest and most impactful journal out there, and so it's a good journal. And here's the other paper here. This one I think gives the coefficients on the model, and that I used to build it. And like I said, as you saw an example before, these are the inputs, the outputs, written description. And I also have a graph in here that show the expected model accuracy if you control like the variables of time, flow, and load, inflow load of nitrogen, phosphorus. You control those, but you change the acres of your wetland. That's what this graph shows. So like on the bottom here, this is like a wetland size of 1 acre versus a wetland size that's 1,000 acres. So as the wetland gets bigger, it removes more and more phosphate. And I put in a little bit on assumptions and limitations. So you know that, like, as any model, there's simplified versions of real world. There's a lot of factors that affect this, many factors, and this is just a model. So don't expect it to be exactly right every time, or a model's never right, but they're useful for kind of seeing big world processes, or understanding systems in a more simplified version. And then if you want to get to the Python code, which was published by the Idaho National Lab, you could go to their unsupported web page here on GitHub, and you could download these models. And so the models that I uploaded in there when I worked at INL, they were built for the ESRI ArcGIS API, or ArcGIS Python interpreter. Sorry about that. And so this one here is designed to work with ArcGIS Pro's Python interpreter, and it relies on a library called ArcPy. That ArcPy is a proprietary library. So if you try and use this script here, it will not work on like with Visual Studio Code, because you can't get that library unless you have a license of ArcGIS Pro. And then this one here, the ArcGIS toolbox, that's if you want to load it on a server, an ESRI ArcGIS server, and run it there. and it does have a license here. This is the stuff that you have to read if you're going to use that license. It's basically open source, and I think it's like not for commercial use, but it could be used for personal things. And but I think you got to give credit or something like that. I don't maintain this. This is what Idaho National Lab maintained. But basically, what I did with mine was when I built it, I created a open source Python version, and I'll put that in the description, the YouTube description, of where you could download from my personal GitHub the open source Python script. And then and what I did with that is I used I took the regression modeling out of there and some of the coefficients that were created from the Python script, and developed it into JavaScript and TypeScript, and uploaded onto my web application, because my web application, it's built upon Angular, and I wanted it to work on the front end, because when you start integrating the front end of the web map application with the ArcGIS REST endpoint server, it's complex and it's slow. It's really slow, and so I built mine with so it works on the front end. So the browser does the calculations and it's fast. You could just enter it in, hit it, and it runs, rather than having it enter in your information, send to a server. Server does a calculation and it sends back, and then the user gets it, and that takes 40-50 seconds. You know, most people ain't gonna wait that long. But yeah, I'll put my GitHub link in the video description, and it's called Native Sci, and GitHub Native Sci is my link. Actually, I could probably show it to you. I have it here. No, we don't have it here. But I'll put a link there. And with that, I hope you enjoy the video. I always appreciate your time. And I want, most importantly, what I want you to take from this is that we could start purifying the water by building these wetlands and improving wetlands. We could purify the water. We're coming in a time where the importance of water quality is increasing, and not only water quantity but water quality. You know, you got to ask yourself, what good is water quantity if it is hazardous or hazardous waste? And when these water, like I showed you those dead zones earlier, when that water goes into the ocean, it basically causes dead zones in these estuaries, which used to be at one time one of the most productive, biologically diverse places on the planet, and it's killing the sea. And so it's really important that we start managing the wetlands and the water. And so that's what I want. That's why I'm putting this video out there, is like I'm hoping you out there will take it further, use this tool, start understanding it, and we start figuring out how to make our streams, managing our streams better. So thank you, and don't forget to like and subscribe. Cleve out.